So from a calculation sense, from a graphing sense, and often from a particle explanation sense, we're going to treat all gases as if they act ideally. That means that they don't interact with each other, they bounce perfectly off one another, and under many conditions, or even normal standard conditions, a lot of gases, maybe even most things that we think of gases, act so close to ideally that it's a very good model for their behavior. But when we account for some of those differences, there is some predictable and some explainable difference in behavior. So when it asks what would deviate the most, we need to understand what causes deviation. Well, one thing that we assume about gases is that the particles themselves have no volume. That's not true. They are matter. They have mass. They have volume. So the particles themselves do take up some space, and the larger the volume of our gas particle, and that would just be based upon atomic size or molecular size, the more it might deviate. The other thing that's often more of an issue, depending on our temperature and pressure, is IMFs. We assume that particles bounce off of one another perfectly, but when they do bounce, if there is significant IMFs, there would be some loss of energy or some sticking together. And on this one, that's the more significant difference. So H2O likely deviates because not only when two H2O molecules are close together do they stick together a little, they stick together a lot. We've got dispersion, dipole, and hydrogen bonding, so they would likely stay close to one another and maybe even stay together or have a more significant loss of the energy based upon that impact. The other thing in terms of particle size, helium is clearly the smallest out of these three particle gases in terms of its particle size. In fact, it is the smallest atom on the periodic table. The only thing that we could have that would be smaller would be a hydrogen ion, but that doesn't act as a gas. That only exists in solution, and really it doesn't really stay like that in solution, which we kind of talk about in acids with hydronium and hydrogen ion. A total digression there. The helium is super small. Both H2O and CH4 are a little bit bigger. CH4 is likely slightly larger than the water molecule with less Zeph, with more atoms on our central atom, but because they're both in the same row on the periodic table, probably similar in size. So those larger particles would definitely deviate more than the helium, and the very strong IMFs in H2O would make it deviate more than the CH4, which is symmetrical and has much weaker IMFs of just dispersion forces. So then to kind of extend what we just said about water, when would it not be ideal? So if we force the molecules really close together in terms of pressure, that's when they start to stick together. So no matter how hot or cold it is, we can force our water molecules together at a very high pressure and it would stay liquefied. But in terms of temperature, when would it not be ideal? Well, it's not an ideal gas when it's not a gas. So if it's at a very high temperature, if we're at several hundred and even thousands of degrees Celsius, those particles are moving so fast that there's not much chance for them to attract one another. But as we cool it down closer to the condensation / boiling point, that's when those molecules are moving slowly enough that when they come close to one another or when they do interact, they start to stick together. So at 100, water vapor or steam would turn into liquid water. So at 100, it would totally be unideal. It would be changing from a gas to a liquid. So temperature's kind of in that ballpark. A little bit above it is when we would be less and less ideal. And then here, this is going just a little bit further than the previous two questions to understand what does it mean in terms of measurable properties to be not ideal. We have xenon water and fluorine. Here, the real pressure or the pressure that we would measure, why would it be higher than the ideal pressure? So as we think about the two causes of non-ideal behavior, it's either molecules sticking together or molecules being bigger than we model them. When molecules stick together, That's as if there's actually fewer particles in our container. And when it seems like there's fewer particles in our container, if there's two water molecules stuck together, for example, instead of having two collisions with the side of the container, they would likely collide as one and just have one. IMFs that are very strong actually often lower the pressure compared to the predicted ideal pressure or the calculated ideal pressure. It's when we account for the fact that particles actually have volume that our pressure goes up. When we assume that they have no volume and they're just these little tiny points flying through the air, bouncing off the walls, we assume there's a certain number of collisions. But when they really take up space, that means that they are occupying more of the container than we model. Therefore, they run into one another more frequently than we would model, and they run into the side of the container more frequently. So that's why in this case, xenon is the one that would have a real measured pressure that's likely to be greater than what we would predict graphically with the KMT or with the ideal gas law. Because the particles themselves are a little bit extra big when they run into each other or other things, they do that more often than we would think that they would. The strong IMFs that happen in water would have the opposite effect here. So we're really looking mostly at size. It's very rare that we have to get to this degree of explanation, but it is important to note that the two factors can have two different effects. And there is a corrected version of the ideal gas law that we might look at a tiny bit that accounts for those differences in volumes and accounts for the differences in pressure based upon calculated IMF strengths and calculated or measured molecule size.